Okay, I think we are online. Good afternoon, everyone, and thanks for joining the BigMedilytics project-sponsored session on improving healthcare through big data, last findings of BigMedilytics. I'm Alexandra Muñoz, and I am a science communicator at INCLIVA, a biomedical research institute based in Valencia, in Spain. And I'm the leader of the communication and dissemination work package of BigMedilytics. First, let me remind you the housekeeping rules for this session. All participants except the speakers and the chairs will be muted by default during this session. And if you want to ask questions, please use the Whova chat and then use the chat of Zoom. You can contact the session facilitator, my colleague Ana Ferrer, if you have any technical issue. And now we can see the sponsors, the organization sponsors and the project sponsors that make possible this event, this edition of the European Big Data Value Forum. And now I would like to present you the speakers of the session. Wiebke Duttmann is a doctor of medicine at Charité Universitätsmedizin Berlin in Germany. She's working as a medical intern and as a research fellow. She's a member of the working group Digital Nephrology. Dr. Dimitrios Boyadzis is a research associate at NCSR Demokritos in Athens, Greece, and the coordinator of the Master of Science in Data Science at the American College of Greece. And George Langs is chief scientist and co-founder of ContextFlow. The agenda of the session is as follows. First, I will make a brief introduction of the project. Then Wiebke Duttmann will present the kidney disease pilot, and Dimitrios Boyadzis will present the lung cancer pilot, and George Langs the radiology workflows pilot. And finally, we will have the discussion and questions. For this part, we encourage you to participate since we would like this to be quite interactive. And now. Now, okay. Now I will introduce the project very briefly because, well, I hope some of you already know the project, and I know some of you maybe have attended some sessions where the project was also presented during these days. So, BigMedilytics is a project funded by the European Union's Horizon 2020 Research and Innovation Programme. The project involves 35 partners from 12 countries covering the main actors of the healthcare sector. The project is working with 11 million patients' health records. The objective of BigMedilytics is to transform healthcare in Europe by using the state-of-the-art big data technologies to achieve breakthrough productivity in the sector by reducing costs, improving patient outcomes, and delivering better access to healthcare facilities simultaneously. The project implements 12 pilots that address 3 different themes with the greatest impact on the sector and covers the entire healthcare continuum from prevention to diagnosis, treatment, and home care. The first 2 themes, population health and chronic disease management and oncology, cover the 78% of all deaths from non-communicable diseases. And the third one, industrialization of healthcare services represents the 33% of the total cost on healthcare spending. During this session, we will present the current status of one pilot for its theme. We will present the kidney disease pilot for the first theme, the lung cancer pilot for the second theme, and finally the radiology workflows pilot. The learnings captured from all these 12 pilots are used to define a blueprint which describes the best practices that need to be followed from both a technology and healthcare policy perspective when rolling out big data solutions for the healthcare sector. The blueprint will ensure that concepts from the pilots will be successfully scaled up across Europe while adhering to strict privacy and ethical guidelines. So now, Wiebke Dutman, the floor is yours.
So, Alexandra, can you stop your presentation, please?
You should now, I think you can now share.
Do you see my screen? So I would like to talk about telemedicine and prediction models in patients after kidney transplantation. Okay. So we have a telemedical service at Charité. The service includes an app, which is of course available for the patient 24/7. Patients can send remote vital signs, including blood pressure, pulse, blood sugar, temperature, weight, and hopefully soon oxygen saturation in blood, remote adherence, remote well-being. We have a medication plan in Germany, in German, the Bundeseinheitlicher Medikationsplan, and we share intake tracking to outpatient physicians. We share laboratory values and medical messages as well as video consultations. So as signed in green, we plan on taking care over our patients during pandemic with laboratory values, including test results on SARS-CoV-2 and oxygen saturation in blood, which is very sensitive for severe causes. We have a telemedicine team, which is available from 8 a.m. to 4 p.m., including me. This is our office, and we are working currently. So when a patient is eligible, we make a profound training on the smartphone app. On a daily basis, we review vital signs, laboratory values, and well-being, as well as changes in medication plan. I will come to that later again. We are kind of a hotline. Technical and medical aspects can discuss with us. We review adherence and support if patient loses a track, and we are communicating very intense between the patient, the doctors at hospital, and home nephrologists. So we started in February 2020. We are supported by 2 German healthcare insurances. We include practically all patients after kidney transplantation, no matter when they were transplanted or how often. And we also take care about patients after pancreas transplantation. And we permanently develop our features and make adaptations due to usability. So a short overview. On the 1st of September, we had 220 patients. Now we are we have about 290, and we seek for 300 with the end of the year. The main age is 55 years old. Most patients with 62.7 are male. As you can see, only 80% are firstly transplanted, or the others have second or third transplantations. The longest one is transplanted or has been transplanted 30 years ago. In red, you can see we screened more than 111 patients to participate, but they didn't want to participate right now. Just when all features are available, then we can talk to them again. Our dropouts are 13. One patient unfortunately deceased. Others just didn't use it. 5 patients, or 3 found the app too complicated, and some other technical aspects. So a little peek on the app. Here you can see on the left hand health data, the well-being. So how do you feel today? We don't want to know if, of course, we want to know a lot about the patient, but we don't want to know if a patient did sleep bad, or the child popped with a football into the stomach and now he has stomach pain or something. It's medical well-being. So if the general health condition worsens, and so on. Heart rate, blood pressure, and when you screen downwards, you can see the other vital signs. On the blue letters show the history, so the patient can document the vital signs he is sending to us for the empowerment. In the middle, you can see the communication tools. So it is just a chat function. You have access to camera and documentation, which is stored in the iPhone or Apple, or now I told everybody what I use, Android phone. And you can see the medication plan. This is a standard. It's a bundeseinheitlicher Dokumentationsplan with a QR scan. So other doctors can scan this code and have at once access to the medication plan of the patient if necessary. And on the right hand, the medication plan is zoomable for practical reasons. This is what we look for in red, the critical values. On a daily basis, we evaluate all vital signs. If a patient has critical vital signs, we get in touch with him or her. Suspicious vital signs in yellow or orange. And in this case, yeah, we get in touch, but sometimes not at once because it's not necessary every time. And in the middle, in green, fine values, and if a patient is fine, we recognize it, of course, but we don't take action. So we build up a trust platform. The patient decide which data can be shared. Patient has to register and award key rights. We use data reduction. We use standardized end-to-end encrypted communication, firewall at Charité, and pseudonymization of data, and HL7 FHIR is our API. This is a little overview. It's a little bit complicated. On the left hand, you can see Charité. This is for hospital physicians. We have an electronic health record called T-Base. I tell you about that later a little bit more, but we share information with the patient, which you can see in the down there, and we share information about the medication. We can change the medication plan of the patient if it's necessary, and the patient can see it in the smartphone app. We get the vital signs. And on the right side, you see NEFR7, which is the electronic health record of MedVision AG. This MedVision AG holds a stack of 60 to 67% of all outpatient care electronic health record systems. Sorry. And these are our partners, and we share our data. And in the middle, you can see the company Medworks.io, which built up the sorry, I had a cold and I have a lot. The Medworks.io hosts the data and has a key for the pseudonymization. So now some more information about NEFR T-Base. It includes more than 6,000 patients. And as you can see, many information about kidney transplants, diagnosis, procedures, laboratory values, and medications. And this is what is elevated in the frame of BigMedilytics. It is in use for more than 20 years now. It is important for controls of quality, identification of study documents and study patients. Information can very easily be extracted by us, and scientific questions can be answered. Now, BigMedilytics, risk prediction. We work together with the German Institute of Artificial Intelligence, Roland Roller, for example, and he set up risk prediction models regarding death, loss of organ, transplanted organ, and infections. And on the base of T-based data and on the basis of the incoming data in the frame of the home measurements, we want to predict loss of adherence. This concept included deep learning and text mining, and is support of medical doctors. And we are currently evaluating these ideas and for sensitivity and specificity. So now I want to show a live demonstration. I'm so sorry. As you can see, this is a T-base. Oh, so I have a little for privacy. Yeah, so this is these are test patients, so you don't see any real patient here. And this is my, the test account of my chef, Clemens Budde, Professor Clemens Budde. And as you can see, here the vital signs he sends to our telemedicine dashboard regularly. And over the time, sometimes he's very stressed out. Blue means a blood pressure, and sometimes this is a well-being, so he's in good mood, he's in bad mood, and a heart frequency is a pulse. And here we can give any information for long-term aspects on the patient. Everybody has to know. Every patient gets who has been seen, which is noted. So now I know I saw his data, and here more information in the T-base, main data, and doctors, diagnosis, procedures, course of information, which will be hopefully soon shared with outpatient care doctors, laboratory values, and the medication plan, which can be changed here, and then the patient gets the Bundeseinheitlichen Medikationsplan on the smartphone app, which is pretty cool. So, okay. So coming back to my presentation. The aim of our digital projects is safety of our patients, because we evaluate for interaction, medication, drug-drug interactions, but also the early recognition of bad vital signs. And we want to improve the adherence of the patient, and so the empowerment, so the patient knows the disease very good, and he can is very sensitive of any symptoms he has, and gets in touch with us if he feels bad, and so on. It is an intersectoral patient care. We want to improve communication between all the people in charge of a patient. Of course, we want to do research with patient data, and the early detection and detection of complication and early intervention. And the final goal is improvement of outcomes and reduction of cost in healthcare branch. So we always won the award of the future of German Society of Nephrology, and we're very proud of this. And thank you very much for the your attention. But it's a big team, as you can see. we all work together, doctors, nurses, software developer. We sometimes talk to lawyers because the data protection concept is very profound. And we have many guest scientists from DFKI and HPI Institute. So thank you very much.
Hello, good afternoon to everyone. I'm Dimitrios Vogiadzis, and I will present the lung cancer pilot. I will share my screen. Okay, hello, can you see my screen? Yeah, okay, thank you. So the lung cancer pilot, I will show you some slides to give you introduction, and then I will make a live demo. The lung cancer pilot, okay. What are our main findings? What is our main research so far? Basically, what we intend to do is to guide oncologists to perform clinical interventions so that they perform clinical interventions in Madrid, the hospital UPM. And the clinical interventions should affect all stages: diagnosis, treatment, administration, follow-up, life and last stage, but to give informed, let's say, opinions or good information, we had to perform certain things. The first is to analyze fine-grained descriptions of clinical notes, which contain many things, including demographic data, medical exams that patients have undergone, notes from the oncologists, and so on. And then we analyze also scientific open data, plus many other things like medical ontologies, and all this information, that is the clinical data and the open data and the oncologies, are integrated in a knowledge graph that keeps growing and contains information about the lung cancer. Now, to analyze notes and scientific open data, we had to employ natural language processing techniques to analyze Spanish text, but also to use natural language processing in English to access the open publications, where we intended to detect entities and predicates that connect the entities between them. The entities refer to biomedical concepts, and the predicates to relations between the biomedical concepts. Then we have performed also predictive analytics so that we can predict drug-drug interactions, especially between oncological and non-oncological drugs, because this might be crucial for studying the toxicity. And also, we had to build data integration pipelines to integrate structured and unstructured information, open and such information into a knowledge graph. So this is more or less how it looks like. We've got multiple, if you like, resources: electronic health records, articles, drug-drug interactions from databases, from the drug bank. And we've got harvesters, natural language processing, followed by indexing, to eventually create a knowledge graph. Meanwhile, we use a multitude of different types of databases. And eventually, what we are doing is to associate drug interactions to toxicities, to survival time, to visits to the hospital, but also to predict new drug-drug interactions. We are trying to do that also. We have had almost 1,000 patients. We are analyzing about 150,000 articles so far, and we have about 300,000 drug-drug interactions related to lung cancer. We're using oncologies. and various data analytics techniques focused on predictive analytics and natural language processing. This is a screenshot of the lung cancer pilot, but I will display in a moment the lung cancer pilot to see what sort of information it presents. Just we have an overview for each patient. We have about 4.5 drugs associated with each patient. Each patient has approximately, on average, 7 toxicities. Each patient has used 6.9 medical services. Medical services refer to the services that the patient has used in a hospital. And each patient is also associated with about 12,000 publications. To accomplish all this, we have 5 partners. There is the Humph Hospital in Madrid, which provides the electronic health records, the use cases, and we perform the medical interventions based on the findings we will provide. The UPM Hospital, the University in Madrid, analyzes analyzes electronic health records, performs statistics and natural language processing. SSR Democritos in Greece analyzes open bibliographic data with natural language techniques, and also tries to perform drug interaction prediction. The LQH University in Germany essentially builds the knowledge graph and performs data mining on the knowledge graph. And eventually, ATC, a software company, is responsible for the software integration of all the components of the pilot that are being built by different partners. Now, for the next part, I'm going to show you an example of the lung cancer pilot. Okay, all this information that comes to the pilot had to be extracted. Unstructured information had to be made structured so that it can be processed by the pilot. So the only thing that you see from the pilot is actually the front end, something that the doctors would see. So for example, I have selected male patients. The stage of the diagnosis 2 and 3, performance starts with diagnosis 1 and 2, and they are taking oncological treatments. So I perform the investigation, and what I'm getting, the first information is about survival curves. For example, I see the different parameters related to survival probabilities. One of them is comorbidities, the most serious it seems. So I can see, for example, if the patient has comorbidities or doesn't have comorbidities, what is the survival probability? And I can see likewise for different parameters. Then I can have some general statistics, again, based on the sample of the patients I have collected. For example, how many are the male and how many are the female patients, the number of patients per stage, and so on. Then I can move to the some more specific statistics that are of concern to the BigMedilytics project. For example, one of the points that we aim to do with interventions is to reduce the length of hospital stay. And for example, I can see very statistical information. What is the hospitalization time based on different parameters. So, for example, I can see here something more interesting, the hospitalization time based on the age, based on different age ranges, and other things. For example, I can see also the influence of tobacco hospitalizations, and this can provide useful information to the doctors to make decisions. Another parameter that is of particular interest to us is the identification of people at risk of developing lung cancer. Identification of people at risk of developing lung cancer. So I can associate this with services they have used, for example, 1 to 6 months before being diagnosed. So maybe the patient went to the hospital. The patient did not know they had the lung cancer, and so he went for a visit to the hospital. And 6 months and 1 to 6 months later was diagnosed with cancer. So we see that here the services that were used based on their frequency before being diagnosed with lung cancer 1 to 6 months before. So we see that immunological services were heavily used, and the other services based on their frequency. Okay, furthermore, the pilot allows us to investigate knowledge graph. For example, I can what is the knowledge graph? It's something that integrates all the information about patients and also open data. And I can filter this out so I can get more focused information based on the problem I'm studying. For example, I'm checking chemotherapy drugs. So the first thing I will see is different publications based on their relevance to the current patient cohort, but also apart from the publications, we have calculated also an index, the number that you just 18.75, which tries, it's a ranking system we have been using, which is based on many parameters like the recency of the publication or the impact factor of the journal or the impact factor of the authors, so that if you like, there's a hierarchy of publications, so maybe you can start focusing first on the high impact publications. Meanwhile, we also provide some index of the publications like the H index, so that there is another way to judge the importance of publication. Furthermore, we also provide drug-drug interactions that are relevant for this patient cohort and for this filtering we have selected. And so these are, if you like, what I'm showing you now is direct access to the knowledge graph. And eventually we can display side effects of the drugs, of the chemotherapy drugs the patient is taking. For example, the carboplatin has vomiting, nausea, and so on. Okay, these are the things I had to cover. Thank you.
All right. Hi, my name is Georg Lang. So I'm just setting up the sharing. All right. So I hope you can see my screen. My name is Georg Lang. I'm with ContextFlow, and I'm also with Medical University Vienna. And in the next couple of minutes, I'll show you a bit about the results of the BigMedilytics project in the context of radiology workflows. And in particular, we were working on a search engine for radiological images. And the reason for that is that we see, or we know then in radiological practice, when radiologists are looking at images, trying to do diagnosis, trying to find and identify findings that are relevant for treatment decisions, that there is a big kind of disparity between the amount of data that they have to look for and look at and the number of radiologists who can actually do that. And so the goals of the project work and the goals of the software that was developed is, first of all, to reduce the time to diagnosis, to at the same time increase the quality of diagnosis, because we are realizing that the landscape of possible diagnosis of disease variants that are relevant if we want to make good treatment decisions is really increasing and getting more diverse. So we need tools that help us to compare patients to other patients in order to figure out what might be a good treatment, what might be a relevant diagnosis for this patient. So speeding it up, improving the quality, and the way to do that we evaluated was how we can help radiologists to get fast access to the relevant information they need for the diagnosis. And this relevant information can come in the form of literature, of information for differential diagnosis, but it can also come in similar cases, in the form of similar cases, because it turns out at the radiology departments across hospitals, there is a massive amount of data being generated in the form of imaging data, CT, MR, and the accompanying reports, the knowledge about what happened to this patient, what kind of treatments these patients got. And we realized that one way to help for the diagnosis and for helping treatment decisions is to enable doctors to look at the patient and then tell, well, these are groups of patients, or this is a single group of patients that are so similar to the patients that I'm looking at right now, that their history of treatment, their outcome, their diagnosis, their diseases are actually helpful and informative when I say something about the patient in front of me. A bit about the underlying research. So there was quite a lot of work on understanding and evaluating how far we can go with extracting data from imaging information, hospital routine data, so CT in this case, from lung CT. So this was work by Johannes Hofmanninger and others, where the goal was to see if we can find groups of patients that are similar in terms of visual information, then check whether this also reflects clinically similar diagnosis, treatments, and other parameters. And it turns out that it does. And so during BigMedilytics, we kind of implemented that software in various sites, and I represent a couple of results that we got and how to do that from the Medical University Vienna and the General Hospital in Vienna, which is a fairly large center in Central Europe, so with about 1,600 medical doctors, about 1.1 million outpatients per year. And importantly for this pilot and for this use case, more than 372,000 imaging exams performed per year. So you can see that there is quite some pressure on doing that efficiently, but also well, because these are typically patients that have a complicated disease where we need help in order to do a good diagnosis. The way that is implemented is essentially that a machine that runs a search engine runs on the hospital side, in the hospital infrastructure, that is connected to the scanners. You see that in the lower part of the slide. The scanners put the current recent imaging data of the patients to this machine that pre-processes and presents that to the radiologist when they look at the data. But at the same time, it then enables the radiologist to perform search with this imaging data in a large case database. And what they use that for is, first of all, to confirm findings that they know about, and also to identify findings that they don't really understand at the first glance, so to speed that up and to help them have confidence in what they are looking at. It does that by pulling up relevant cases in terms that they are similar cases where we know the diagnosis, where we know the reported findings, and it supports them in the differential diagnosis. If there are diseases that look similar, but where there are a couple of features that really help to differentiate between one and the other disease. The underlying methods and the underlying technologies are, first, that there is the need to use, in this case, machine learning on the imaging data to find similarity functions between images, because it's not really helpful if you just show them a couple of lung CTs just because they're looking at the lung CT, but it's necessary to figure out which of these sometimes very subtle visual signatures that are really related to disease we can use to match similar cases that also have similar diseases or similar characteristics in terms of the staging of the disease. A lot of the variability that we are observing is just very natural, normal variability between people, and machine learning we need in order to figure out which of these subtle signatures that are riding on top of this big variability distribution, big variability, that are actually helpful with we want to find the right disease and want to identify the right disease. So that's one package, designing this similarity function and learning that from clinical data. And the second technology is to do that fast, to do that quickly, because we essentially have to do that when a person, a user, clicks on an image position, and the moment these search results are presented, we have little less than a second. And during this second, this comparison, this similarity calculation has to happen between this query patch and a couple of billions of images of image patches that are living in the index in order to perform the search. So what happens in practice when people use that, they mark a region of interest, then this comparison is done. So there is a huge index of image patches. So each of these image patches doesn't represent an entire patient, but really just one position in a patient, because not all of the lung looks the same. So these diseases, they affect certain areas of the lung and sometimes really focal lesions. That means this comparison gives us a way to map out the similarity between the query patch and the corresponding images, or the images in the index on different areas in these images. So we are really able to say, well, this finding is distributed in this or another way in these other cases. And this in turn gives us a way of saying, well, this is a set of cases, this is a cohort of patients that really look different, are similar to the patient that I'm diagnosing, that I'm reading right now. Now, where it comes in that these are past patients where we know about the diagnosis, the treatment, and the outcome, that also means that we can present some statistics that give us indications about what happened in these patients, what are the diseases, and what are the findings. So let's have a look at how that looks like in reality. So on the left-hand side, you see the case that the radiologist is looking at right now. So this is a slice in a CT image. On the lower part, you see two projections that basically help you to navigate. And when you mark a region of interest, you see that here. Then what happens is within about a second, the search is performed. So the search pulls up and identifies patches in this case, over 5,000 patients. So there's a couple of billion patches that are really similar to those that you have clicked on. You also see that it categorizes these patches in what types of findings that might be. So it might be cyst or emphysema or bulla. And since these are past cases where we know what's in there, we can say that for initial patches, but we can also say that for the entire cohort. So we can give some indication what's the likely finding is that we are looking at. On the lower part of the image, on the left-hand side, you see that it also identifies the distribution of this finding, in this case, a cyst across the case that you are looking at right now. And on the lower part in the middle, it also allows you to kind of dig a bit deeper into the individual found cases to look at how this finding is distributed there. Is it like a big patch, or is it lots of local focal lesions that are distributed across the lung? And that's really helpful because it shows you what it might be, but it also gives you the evidence to check back if that's really plausible when you compare by yourself as a radiologist the case that you're looking at and the cases that the search engines identifies as most similar. And these are also the cases based on which the system gives you some suggestions. So radiologists like that they get suggestions, but they also get the evidence. They also are able to check whether this is really the right match or whether maybe the second ranked finding is the right one. And on the right-hand side, and that's really most important for those where there is a lot of time pressure, based on these findings that we have identified, we also can give some differential diagnosis information. That's necessary because sometimes you have to check for a couple of additional findings. Sometimes you also have to look outside of imaging data to get the information to perform the final diagnosis. And this is something which we can already tune and prune down to what is relevant based on the findings that are identified in the case. So the idea is to present relevant information right when they open the case or when they pick certain areas of interest in the imaging data. So this is a tool that's what we are evaluating in BigMedilytics in a couple of sites, and one of them is the General Hospital in Vienna. And I'd like to close with briefly also pointing out that in the course of this work, of course, it turned out that some of this functionality that is running under the hood is also helpful in, for example, quantifying some of the patterns that have been relevant in diagnosing and assessing patients suffering from COVID-19. And so what happened during March and April was that we kind of pulled some of this machine learning functionality from the system and created a tool that allows for quantitative reporting and decisions on these patients. And with that, I'd like to thank you for your attention, and I'm looking forward to questions. Thanks.
Okay, thank you to all the panelists. And we have some questions in the Huba chat. Let me see them. Wow, we have some questions. So the first one, I think this one is for Wiebke. What is or can be the role of AI in telemedical care of your patient? For example, regarding faster intervention. And it mentions also, and is the analytics done only centrally or also on the patient side?
So on the one hand, the T-based data I mentioned, the electronic healthcare record we use for more than 20 years. These data are the basic or basis for prediction models on graft loss, death, and infection. And on the other hand, we have the incoming data which are sent by our patients within the smartphone app. And this is a prediction of loss of adherence. So did I get the question right? Or?
Okay, and there's another one. Which forward-looking analysis predictions do you generate with your tool?
Could you say it one more time? Which?
Forward-looking analysis predictions do you generate with your tool?
Yeah, it's our colleague from DFKI, who's not here right now, is doing all these procedures. We are the medical part, so actually I can't answer this question because I don't perform these kind of analysis.
In this case, they can reach or email us.
Yes, and I can forward the email to my colleague, and he can answer.
Okay. And another one for you.
Okay.
Are you seeing improved outcomes from use of this system? Are these improvements aligned with the major causes of adverse outcomes already known in practice?
Yes, we actually got over time. We started in February. Over the time, we became more and more sensitive to the way vital signs change. And we really called, at the beginning, we called our patient every time and asked what's going on. Do you feel fine, and so on. And now we are very sensitive, and we pick out sick patients very good and help transferring to hospital or give help with problems. Yeah, I'm a doctor too, so I can help, right? And it doesn't, a blood drawing or something is not necessary. And I think, yeah, we just started 6 months ago, and I think we can see more impact as much patients are included and participate and really send their vital signs. Some patients need to be pushed from time to time so that they participate and send regularly the vital signs. But then I think we can help very much. So yeah, we help. We can help.
Thank you. Thank you. And one question for George. The first step is for user to select a region of interest manually. Why can this be done automatically, learning from the billions of index subsector images?
Great. Thanks. Yeah, I think that's a very good question. So why do you have to mark it up in the images and not just run the search beforehand? So that's true. And right now we are actually doing that, because when we are comparing the images with the query images, we also get an idea about what might be in there. And we also have kind of a way of telling what are the hotspots in the images that carry different patterns. And so we can basically right now, what happens when you open up a case, it already opens up together with search results that are triggered by a couple of hotspots in the imaging data that were really very wide out of the normal spectrum. So it's right, and that's actually radiologists like that because they already start with helpful information. And yeah, it's a very good point.
Yeah, and this person also asks what image recognition approach is used. He mentions ZB ResNet.
So yes, in principle, this family of approach points to an idea what is there at this point in the imaging data. And the second job of deep learning or evolutionary neural network structures is to come up with a good similarity function, and this type resonates or whatever works. These are the tools that are on top of this and translate this imaging information into feature vectors that allow us to compare them efficiently.
Yeah, I think the image was frozen for a moment. Well, I don't know if you answered to, there's another question, and someone, another person is asking, what kind of infrastructure is required to achieve the high speeds that permit real-time comparison?
So the infrastructure, and that was actually also quite a lot that we learned while we were implementing that at hospitals. So the infrastructure is at the hospital side, it needs a virtual machine with some CPU processing power, but not a lot, like a modest amount of CPU processing power, not GPU processing power, because right now that's not really realistic to have that at all hospitals. And the pre-processing, a lot of the processing happens between the time when the scan is taken and the time when the user opens the image. So that's a couple of minutes at least time that we have in order to perform the pre-processing. That's happening on site. And then during the search, what happens on site is the extraction of the feature vector or the descriptor that captures the imaging information at the point where the user clicks, and this is sent out, and then that happens in our infrastructure, the comparison between this feature vector and the index of example cases. So there we can basically use our own infrastructure, which is strong, but at the same time, a lot of this was not just solved by strong infrastructure, but just by the way this index is structured and captures the similarities, so that the comparison is very fast, basically. So on site, it's a modest virtual machine with some working memory to process the images between the time of scanning and the time of opening them. Then after that, the processing power on site is very limited, and most of that happens off site, but really the only thing that leaves the hospital is this 20 element or 40 element feature vector, and the comparison then happens on the outside infrastructure.
There are no questions right now, so you can keep on posting questions. We have like almost 7 minutes to finish. So in the meanwhile, I would like to ask a question to Dimitrios. Will the knowledge graph of the lung cancer pilot become publicly available so that it can be used in other hospitals?
Hello. The plan is to release the open data part of the knowledge graph, which refers to publications, whereas the other part, which refers to the electronic health records, it cannot be released for various reasons, including data protection reasons.
Let's see if there are other questions. From the attendees. Okay, so Another question, Dimitrios, what is the role of data analytics in the lung cancer pilot?
Okay, thank you. We perform data analytics at various stages. First, we perform natural language processing to scan electronic health records in Spanish, which contains both structural and unstructured information. For example, there is a doctor writing notes on electronic health records, which has to be analyzed to detect precedents, to detect medication being used, etc. We also performed analytics, natural language processing on the open publications from PubMed to detect biomedical entities and links between them. Also, we perform drug-drug prediction interactions. So we try to predict new drug interactions which have not been recorded before. These are the main stages of our for predictive analytics.
Just checking if there are more questions. Please keep on posting questions. We have some minutes still, but well, I will ask George in this case. Have you tested the software in a clinical setting, and what do the radiologists say?
Yes, so thanks for the questions we have, and we are testing it right now. So what we did, we compared kind of realistic settings where they have to read cases with and without the system. And what we found was that on one hand side, they like it in order just to explore the cases and see what similar cases are there. Sometimes in university settings, they also like to use it for teaching or like for preparation of teaching to pull similar or interesting cases. But for the actual reading, the two things that they realized and that are basically consistent with what we aimed for is that it actually does speed up the search. So once they perform search on an image, to do it without the system and to do it with system, there is really a big gain in time when they use the system because it's just prepared. And the other one is that for the difficult cases, it also helps them to get it right more often than without the system. And so this was a clinical setting in which they tried it out and are still trying it out across multiple sites. And so we learn a lot from what they tell us about what they would like to have changed or what they would like to have in terms of additional functions. So yeah, it's running in a clinical setting. And I think it's important because a lot of the things we now know what's useful and what's not useful, we really only know or started to understand once it was running in a clinical setting.
Thank you. I think now we should finish because there's another session after this one. So thank you very much to all the speakers for your presentations, and thanks to the organizer to make this session an event possible. Thanks also to the attendees for joining the session. And the recording of the session and the presentations will be available afterwards. And we also recommend you to visit the BigMedilytics website to be aware of all the project updates. And feel free to reach us out in case you have any questions. You can write an email to info@bigmedilytics.eu. And that's all. Thank you very much and have a nice day.
Thank you. Bye.
Thank you.
Thank you. Bye.
Bye.
Thanks.